All right, Kevin McManus. He's going to give a talk on hunting for runaways from the Hyades, Pleiades, and Alpha Perseus open clusters, and other interesting Gaia data analysis. Gaia. Kevin is a practicing data scientist applying data science techniques to astronomical phenomena. He has been researching open cluster membership as an astronomy student at the University of Colorado. He holds a BA degree in economics, math minor, and a master's in business administration. After a 25-year career at Hewlett Packard, various software engineering and program management roles, he decided to get in touch with his inner econometrician.
Econometrician, please.
Econometrician. I'm just an engineer. I'm sorry. And rebranded as a data scientist. Kevin has had data science engagements in business intelligence, product recommenders, and neural network image object detection. He currently volunteers at Little Thompson Observatory as a telescope operator and data scientist for LTO's radio telescope team. He is studying astronomy at University of Colorado in Boulder, Colorado. All right, Kevin, go ahead.
All right. Well, thanks for the intro, Rich. And yeah, I'm flattered that all these references to WWV in Fort Collins, Colorado, because that's where I live. And I like to ride my bike around the antenna farm of WWV. It's a wonderful country to ride a bike around if you're into road biking. So anyway, yeah. So what we're going to talk about today is we're going to look for runaways in the Pleiades and Alpha Persei open cluster. Hyades didn't make the cut. That was originally planned, but I deleted it out of the presentation because I wound up with way too many graphs. And so Hyades got the axe. So we're gonna look for runaways in the Pleiades and Alpha Persei clusters. We're going to use Gaia satellite data to as a source catalog for information about these about the members of these clusters, and then try and find the ones that got away. So that's the agenda. And tell me that you're seeing my screen. You seeing this, Rich?
Yeah, I see it fine, and you're coming in loud and clear.
Okay, great. All right. So here's a overview of what the presentation, how the presentation is going to flow. We'll look at the online Gaia catalog. That's the source of information about the stars. We'll look at some membership lists and where those membership lists come from. The membership lists provide training data for our modeling and filtering. We'll do a catalog search, and the catalog search will give us a whole slew of stars to look at. And then from that batch of search results, we'll go through a filtering process to identify candidates, and out the other end comes the actual candidates. So that's the flow. So let's move into it here. Okay, so the Gaia catalog. Okay, so first of all, the Gaia catalog is a data product of the Gaia spacecraft. Gaia spacecraft is a product of the European Space Agency. Started its mission in, I think, 2013, might have been 2013, December of 2013. And it's floating around up there in space, and it's providing very detailed, very precise measurements of objects, stars mostly. And it provides photometric measurements and astrometric measurements. So photometric measurements are measurements of the star's color in different, the light emitted by the stars in different color bands. The astrometric information is information about the star's position and the star's motion. And we'll use both of those pieces of information about each star to figure out whether they properly belong to either the Pleiades or the Alpha Persei cluster. All right, so the eyepiece of our little telescope is this online catalog called the Gaia Archive. And from the Gaia Archive, you can, oops, what is this? There we go. From the Gaia Archive, you can do a catalog search. you can type in a pretty advanced, very complicated search, and you input your query there, and out of that you get a big pile of search results. Submit the query, and you get a set of search results. In our case, we get something like 100,000 search results for the Pleiades, and 300,000 or so search results for the Hyades. So we'll look at those in a minute. Okay, so then we need training data. So we need to know what we're looking for, and that comes from data that's provided from known members. And so who's to say what the known members are? Well, so within the Gaia world, there's a bunch of papers. So in 2018, the Gaia people came up with what they call Data Release 2, and associated with Data Release 2 were a whole boatload of papers that were published in various astronomical publications. And there's one here that I use a lot, at least for this project. I use this paper sort of day in and day out. It's circled there on the right. It's called the Observational Hertzsprung-Russell Diagrams. Is that you, Rich? Are these diagrams named after you? No. It's a little joke there.
They have two L's on their name, so they're not. They weren't sure of themselves, so they had an extra L, but that's a different story. Go ahead.
Yeah. Okay. All right. Anyway, so this particular paper provides just a wealth of information about clusters in the solar vicinity. Let's move on. And so from these two papers, this particular paper was published in Astronomy and Astrophysics. It's available online. The whole paper is available online at the URL that I show there. And among other things, the paper provides membership lists for 9 nearby open clusters, including the 2 we're looking at, and about 30 globular clusters, and also some summary astrometric solutions for the clusters. In other words, if you talk about the Pleiades, Pleiades isn't just one star. The Pleiades is 1,300 stars, at least according to these guys. And so when you talk about the location of the Pleiades, you need some summary measure of where the Pleiades is. Anyway, that information can come from this paper. Okay. All right. So when we query the Gaia catalog for the members of the Pleiades and Alpha Per cluster, we can plot the results on an HR or color magnitude diagram, and the results are shown on the slide. The left slide is the Pleiades, the right side is Alpha Per. And what's interesting about these 2 diagrams, one of many interesting things, is that the HR diagrams, the main sequence of the HR diagram for these 2 particular clusters, it's very well defined. And you'll see, I hope you can see my cursor here. The main sequence here, it's pretty thin. You have a few stars above the main sequence. You can see stars at the main sequence turn-off point. They're moving up to the upper right. And so for both Alpha Per and for both Pleiades and Alpha Per, the diagrams are very well defined, which is good news. Okay, so keep that picture in mind when we look at some of the next things. Okay, so now we're going to look at the search results. So we have the known members, and now we query the catalog. We query the catalog for stars that might be runaways from those 2 respective clusters. And the way we did it, the way we do it here is we do a 25-degree cone search centered on the cluster centers. And so that 25-degree cone search comes out in these blue and red dots. And these are the actual positions of the stars that were returned from the search results. So there's 107, call it 108,000 stars for the Pleiades, and there's 292, call it, search results returned in the vicinity of Alpha Per. And if you got your magnifying glass out and looked at this diagram very closely, you would actually count 1 would count, not you, 1 would count 292,000 stars in there. Okay. And then, so just for orientation purposes, these sort of bigger blue dots here, these are the larger stars in Orion. And so what this shows is the area of the sky that we're looking at. It's a little bit to the east, I guess that is, or sorry, a little bit to the west, I guess that is, of where Orion is. A little bit to the north and a little bit to the west of where Orion is. Okay. And so in constructing the search results, then I put on distance constraints. And the center column in this distance constraints table, this is the distance to the cluster center. The center column is the distance to the cluster center, and that comes from the paper that I mentioned previously. So in the case of Pleiades, 136 parsecs. In the case of Alpha Per, 175 parsecs. And so the the red dots, in the case of Alpha Per, the red dots are constrained to be within 87 parsecs and 262 parsecs. And what is that? That's 50%, right? So that's basically 50% of the mean distance to the objects. All right. So basically, what we're going to do is we're going to look in two cases. We're going to look in first the blue dots, the blue search results, then for runaways from the Pleiades, and then in red dots for runaways from Alpha Per. And in the Pleiades case, we have 108,000 stars to look at. And in the case of Alpha Per, we have 292,000 stars to look at. Okay. So now let's look at the HR diagrams of what we got back from the search results versus versus the known members that we had from the previous slide. The search results are plotted in the same scale in light gray. If I plotted them in any darker color, they would just you wouldn't be able to see anything, right? They'd just be this big black blob. So anyway, they're plotted in light gray, and the known members are plotted in blue. And so you can see there's quite a bit of difference between what we consider to be the known members and what we got back from the search results. There's a lot more width here in the main sequence. There's some stuff going on up here towards the end of the main sequence. It's a little hard to see because it's plotted so lightly, but there's a bunch of stars up here on. I think this would be called the red giant branch. These are where where other stars take off from the main sequence, and they evolve more and head towards red giant land. This is the path that they follow. So anyway, so there's some stars up there. And the same is true in the case of Alpha. Search results returned from Alpha Per. You see a lot of stuff. You see a lot of stars here starting to take off on the red giant branch. And then there's a whole bunch of crud down here, a whole bunch of stars, search results down here. These are typically going to be stars whose Gaia data is not very accurate. And so there's quite a bit of uncertainty about these stars, but we'll see later that these stars will get kicked out of our candidate search. So anyway, so that's what the search results look like. Okay, excuse me. Okay, so now part of this exercise is comparing the motions of the stars against the motions of the known members. And so in these two plots, we plot the proper motion in right ascension, that's the x-axis in the plot, against the proper motion in declination, that's the y-axis. And then I overplotted again. I overplotted the known members. So the blue dots are the known members, and the light gray guys are the stars, 109,000 and 296,000 whatever stars that we got back from the catalog search. And so you can see that the known members are concentrated. The known members are concentrated with their proper motions. And that's no accident, because one of the ways that these known members were selected was in the paper that I referred to earlier. One of the ways that the known members were selected was by the similarity of their motions on the sky. So the idea is that the members of the cluster, they all move together. That's why they're a cluster. They all move together. They were born in the stars formed in the same place. They all move together. It's all one big happy family moving through space. And this diagram shows it. The dotted red lines are the published proper motions for the Pleiades and for Alpha Per, and you can see that the dotted red lines just exactly go right through the middle of the known members. So the known members are down here, but the bulk of the search results are way up here. And the same is true in Alpha Per, that the known members occupy a tight cluster around looks like let's call it 22 milliarc seconds per year in right ascension and about minus 25 degrees in motion and declination, milliarc seconds per year. So Alpha Per is down here, but the bulk of the search results are up here. All right. Okay. So now let's move on to candidate identification. So how are we going to look through those search results and figure out which of those gray dots actually really ought to be a blue dot? Okay. So the way we do it, there's 3 levels of qualification here. One is what I call travel time, and the travel time is the time needed for the star and the cluster to achieve their current observed separation. The time needed to achieve that separation, it's got to be within 20% of the cluster age. So the assumption here is that the runaways got kicked out through some gravitational interaction. They got kicked out when the cluster was formed, and so if we know the age of the cluster, then the time for the star and the cluster to achieve their current on-sky separation has got to be within 20% of the age. Okay. The next criteria is called the coeval. The idea here is that the star and the cluster, they need to be near each other when the cluster formed. Okay, it can't be a runaway if the star was never anywhere near the cluster when the cluster was formed. So we got to look at where the star was and where the cluster were back in time, and if they're within shouting distance of each other, well, then that increases the chance that they're a runaway candidate. Okay, and then the third criteria is the color magnitude. So the candidate, for a star to be considered a candidate, it's got to fall in the right place on the color magnitude diagram, right? It can't be in some location where none of the known members are. It's got to be consistent with the positions of the other known members of the cluster. All right, so we're going to take a look at each of these 3 filters, or each of these 3 criteria individually. And but first, we have a teeny tiny problem to deal with, and that is the analysis that follows, the travel time and coeval filtering. We carry it out in 3D Cartesian coordinates, and in order to transform the data that we get back from Gaia catalog requires a 6-parameter astrometric solution for each star. And the 6 parameters that you need are the right ascension, declination, parallax, proper motion, proper motion in right ascension, proper motion in declination, and radial velocity. So you need all 6 of those parameters to be able to figure out the 3D position in space and the 3D velocity vector in space in order to move the star around backwards in time. So the big problem is that only about 1/6 of the records in Gaia provide that measurement of radial velocity. So, what's a data scientist to do? No radial velocity, no problem. So basically, what we do in this case is we create a range of radial velocities. So created a range of minus 200. Oops, that should be km per second. Oops, sorry. Created a range of radial velocity. So from minus 200, that should be kilometers per second, sorry, minus 200 kilometers per second to positive 200 kilometers per second. So that range, that's a huge range. If you look at the measured radial velocities for the stars that are in the catalog, this minus 200 to positive 200 is going to encompass them all. So anyway, so we compute this range of radial velocities, and then calculate these relationships supposing that the star had that particular radial velocity, or it had a radial velocity within that range. So so for every value within the range, we do the calculation and we figure out what is the travel time and is it coeval with the cluster center. Okay, so that gives us the following, gives us this cool graph. Okay, so travel time. To repeat the definition, the travel time is the time needed for the star to achieve the current separation from the cluster center. And so that time needs to be within 20% of the cluster's age. So the graph here illustrates what's going on. So the x-axis in the graph is the range of radial velocities over which we are evaluating the travel time. And previously I said the range was from -200 to +200. Well, once you get, once you get past about -10 and +10, the graph's not very interesting, right? It just kind of flattens out. But in around, at least in this case, starting at around 5.5, the graph gets pretty interesting. So the x-axis is the range, truncated range of radial velocities that we evaluated these relationships over. The y-axis is the travel time, and so the black line, the thick black line, is the set of pairs, radial velocity and travel time pairs, that explain the current separation. So in this case, this particular star, whose Gaia ID is this big hairy number ending in 5808, this particular star is 38.77 parsecs away from, it's observed to be 38.77 parsecs away from the cluster center alpha per. Okay, so that's the current separation, 38.77 parsecs. All right, and each point on the black line is a pair of radial velocity and travel time that it would explain that current separation. So if the star's radial velocity was 5, the travel time for that 38.77 parsecs would be 40 million years. This is these are tens of millions. The y-axis here is tens of millions. So the travel time would be 40 million years. So now this particular cluster, again from the Gaia paper previously, the age of the alpha per cluster. No, I didn't write it down here. The age of the alpha per cluster. This is 70 some million years, and plus or minus 20% of that 70 million years gives you up to about 85 and down to about 57 million years. Right. So this blue bar. This is the age range. This is the travel time that we're looking for. So we're looking for a travel time that's somewhere between, call it 5.7 and or call it 57 and 85 million years. We're looking for a travel time that's in that blue range. And so the yellow bar here is the range of radial velocities that give us travel times that explain the current separation. So if this particular star's radial velocity, measured radial velocity, was between, say, 5.5 and let's call that 6.25, then the travel time from the cluster center to where it is now would be somewhere along this black line. So that's in the good zone, right? That's where we want the travel time to be. All right. So that's travel time. So now let's look at coeval or coeval, and this is kind of like. This is like contact tracing for stars. So if alpha per had an outbreak of coronavirus, the question is should this star be worried? And so to conduct this analysis, basically we construct a look back time, and actually in this case the look back time is just the negative of the travel time. We construct a look-back time and we project where both the star and the cluster were at each point in the look-back time. It's basically constructed over this whole grid, right? So this two-dimensional grid. So look-back time versus radial velocity, and we look back over that time, And then we, at each point where we evaluate this relationship, we calculate how far was the star from the cluster. And so, for example, like at the head of this arrow, again, if the radial velocity was 5.5 kilometers per second, and the look back time was 10 million years, if we look back 100 million years, the separation of the star from the cluster would be denoted by this gray shaded area, which on the color scale is between 20 and 50 parsecs. So that's pretty far. That's pretty far for us to consider that star is part of Alpha Per. But actually, if you look in here, here's a region where the separation between the star and the cluster is between 5 and 10 parsecs. So that's pretty close. And so yes, so if Alpha Per had an outbreak of COVID-19, then yes, this star probably ought to be worried, right? Because they were in the same place at the same time, right? Okay, so let's see what that does to our search results. We apply both these filters together, and you can see again the gray dots are the several 100,000 search results. The blue dots are the known members, and now we have some acme. Right now we have some red dots, and so these 3 red dots in the case of the Pleiades, these 3 red dots are the ones that satisfy the travel time and the coeval filters. And in the case of Alpha Per, we got about 40. Actually, no, I think we got about 50. So these are all potential candidates, at least according to the 3-dimensional Cartesian motion analysis. All right, so that's what we got. And you'll notice that that's a huge filtering, right? We went from several 100,000 stars down to, we went from several 100,000 stars down to about 50. So it's a pretty tight filter. All right. So the next thing is, how do we evaluate the color magnitude? And the question to answer here is, does the candidate star land on a place on the color magnitude diagram that's consistent with the known members? So to answer that question, we construct color magnitude diagrams as before, fit a kernel density estimator over the known members, and some parameters of the kernel density estimator. It's a 300 by 300 grid, and so that gives us this color magnitude diagram here on the right. And you can see the lighter the color, the denser it is. And so you can see that this light color here corresponds to a lot of stars being here, and it kind of peters out as you go up the main sequence. And as you get up here towards the top, there's almost no visible density here. So we construct this kernel density thing here, and we pick a density threshold. We pick a density threshold such that some arbitrary number like 95%, 95% of these stars would fall on a place that's above the threshold that we picked. And so when we go to evaluate a particular star's candidacy, we look at where it lies on this kernel density. We figure out what its density estimate is, and see if that density estimate is above the threshold. And then that tells us whether the candidate star is consistent with the known members. And so you'll see on the next slide what that looks like. All right. So again, gray dots are the search results. Blue dots are the known members. And if we just applied the color magnitude model in isolation against the search results, the red dots are the ones that would pass. And so you can see how this follows along the main sequence of the known members. Okay, so that's what it looks like in isolation. Now, drum roll please. Now we'll look at it. Now we'll look at the actual runaway candidates. Okay, so if we apply those three filters together, what do we get? Well, so this looks a lot like the last diagram. In the case of the Pleiades, the three candidates that we identified from the motion analysis, the three candidates survived, right? So they're still in the mix. And then if you remember from the Alpha Per, we had a couple of stars down. We had at least one star over here in white dwarf land, and we had a couple of stars down here, and they got eliminated. And so what we're left with is these 40 stars, and I think there's 40 stars. There's 40 stars here that fall along the main sequence of Alpha Per. Okay, so these are the stars, at least according to this analysis. These are the stars that are potentially runaway members from the Pleiades and Alpha Per, respectively. Okay. All right. So now let's go back and look at our other diagrams and see where these stars line up. The top two graphs here are just the the top two graphs are the on-sky position. Same color codes as before. Gray is search results, blue is known members, and the red ones now are the candidates that we found. So we found these three candidates kind of far away from the center of the Pleiades. And then we found these members here kind of far away, kind of scattered about Alpha Per. But what's interesting is that these, if you drew an ellipse around this Alpha Per and extended that ellipse, it kind of goes like that. Kind of stretch your eyes a little bit to see it, but they're sort of in the same plane, or same sort of elliptical shape. So there's some astrophysics going on there. I can't really quite explain it. But then if you look at the proper motions, then the proper motions are also pretty interesting, in that the three stars that we found with the Pleiades, the proper motions are not terribly inconsistent with the known members. The proper motions aren't way up here and with the masses. And then with Alpha Per, the proper motions are just all scattered. They're scattered around, but they're scattered around where the proper motions of the cluster members are. They're not up here. Okay. And then last but not least. Okay, so now if we look at the distance from center, how far are these candidate stars away from the center? You can see from the graph that the candidate stars are, they're a good deal farther from the center than the known members, and they are, after all, runaway stars. So that's not a surprising result at all. In the case of Alpha Per, some of the candidates are not as far as the most extreme known member. So this here would be the most extreme known member. It looks like he's about let's call it about 45 parsecs away from the center. And these guys here are all within 45 parsecs of the center, and then these ones are more extreme still. So what this is telling me is that the results we're finding they're not inconsistent. They're the results that we would expect. The colors are consistent with the known members. They were in the same place at the same time when the cluster was formed. And their current separation is explained by a plausible radial velocity. Okay. So let's get this next slide. So conclusions. All right. So we found three candidates among 107.9 thousand stars in the vicinity of the Pleiades. We found 40 candidates among 262,000 stars in the vicinity of Alpha Per. And without Gaia actually reporting the radial velocity of the stars, these candidates will remain candidates as opposed to full-fledged runaway members, right? So we've identified necessary conditions for these stars to be members, but we haven't identified, we don't have sufficient conditions yet. So with any luck, this problem will be solved here in the not too distant future. Gaia Data Release 3 looks to provide radial velocity for many more sources So hopefully we'll get many sources in the search results that will actually have the full astrometric solution, and we expect this in 2022. Supposed to be 2021, but due to the unprecedented conditions of COVID-19, we didn't get it. So anyway, so hold on tight till 2022, and at that point we might be able to confirm whether these stars actually are indeed bona fide members of their clusters. So with that, turn it over to you, Rich. Back to you. Any questions?
Anybody have questions? I do have a question. Do you know of any physical phenomenon which would have caused them to become runaways?
Well, there's all sorts of chaotic gravitational interactions going on when the stars are formed, right? And so they're accreting mass from the surrounding molecular cloud in which they're forming. I think they're exchanging mass among each other, and so it's pretty chaotic in the early stages, and there's some mass segregation going on too. I think the stars that get kicked out tend to be the low mass stars, and so it's the rich get richer and the poor get kicked out. I think is what's going on, and so. Yeah, so what that says is that the stars we really ought to be looking for. The stars we ought to be looking for are going to be the low mass stars that are going to be down here on the HR diagram, these guys. And there's probably a whole bunch of stars that, brown dwarfs that are going to be really dim that Gaia doesn't pick up. So there's probably a whole bunch of stars out here that are former members of Alpha Per that got kicked out.
All right. Go ahead.
Any idea why the Perseus cluster tends to kick out a lot more stars than the Pleiades?
I don't really have an opinion on that. I was somewhat surprised to find, where's my slide? Oops. Basically, we got almost 4 times as many stars back from the search result. I mean, it's essentially the same search results parameter. So we got, essentially 4 times as many stars, 3 times as many stars. Sorry, 3 times as many stars back from the search results. And so I think we have that, and I don't have an explanation for that. I don't know why that's the case. So one reason is, one reason why we're finding all these might be due to the fact that we just have more stars to look at. But beyond that, no, I don't really have an explanation for that. It might have something to do with the size of the cloud out of which Alpha Per formed versus the size of the cloud out of which Pleiades formed. There might be mass differences there, where a lot more stars formed in Alpha Per and then got kicked out. Another thing too is that the membership list for Alpha Per is about 700 or 800 stars were identified as members of Alpha Per, and Pleiades is about 1,300 members, and so. It may be that the guys who put the Gaia team that put the membership list together, it may be that they excluded members that really should have been members in the first place, and I'm picking them up as runaways.
Okay. Anybody else have any questions for Kevin? Well, outstanding work, Kevin. Every time I see this thing, I want to go jump in and grab data, and I wouldn't know what to do with it.
No, it's the Gaia data. The Gaia data is a lot of fun to play with, and it's really easy to access, and it's quite easy to write Python code that accesses the Gaia database, and then you can pull it into a Python workspace and pound on it to your heart's desire. So yeah, it's good stuff. A lot of fun.
Everything you just said is easy. Is not. All right. So
it's easy after you've done it for a year.
Yeah, that's what I'm thinking.
Yeah.
All right.
Okay.
Excellent work, Kevin. Thank you very much.